And here we go. So guys, today what we're going to do is we are going to get into a new topic which actually draws on a lot of the stuff that you've learned before about weak equilibria, but everything that we've done up until now with weak equilibria has been weak acids and weak bases. Today what we're going to do is slightly soluble salts. So guys, here's the way that this goes. Up until now, we've been saying that salts fit into one of two categories, right? Either they're soluble, which means they dissolve, or they're insoluble, which means they don't, right? Guys, it turns out that it's actually not that simple. So for example, silver chloride, right? Soluble or insoluble in water, silver chloride. Insoluble. It's one of our exceptions to the rule. We understand that all of the halogen salts are soluble in water unless they're bonded to silver, lead, or mercury, right? And so we say that those don't dissolve. Guys, it turns out that's not true. I know I'm sort of bursting your bubble, but silver chloride does dissolve in water. Just not very much. Guys, it's so small that we consider it to be zero. So we're not changing the rules. Silver chloride does precipitate if it's formed from a double displacement reaction. But guys, the thing that we are now going to add to our understanding is silver chloride does dissolve a little bit. And so what we're going to do is we're going to talk about these things that we call slightly soluble salts. Many of these salts we've never talked about, but guys, some of these salts we have talked about and said that they don't dissolve when in fact they do dissolve a tiny little bit. So we're going to open you up to this idea that some of these insoluble salts do actually dissolve a bit, and then we're going to describe it mathematically. So guys, it goes like this. So when we talk about these salts that are slightly soluble, we're going to solve these just like any other equilibria. It's just that they have one additional little tricky bit to them. So guys, for example, try this. Calcium fluoride. So guys, here's what I need you to do. Here's what you need you to do. Write the balanced equation that represents the dissolving of calcium fluoride. And then write the Kc expression for it. No, this is a slightly soluble salt. By the way, guys, just so you know, we're probably going to be done with new material here by like 11:15. So you're going to have a ton of time to get your homework done today. All right, taking my life into my own hands, I'm going to try to draw. Or just write. I did. Yeah, so, oh, I remember what it was. So during lab last time, we were trying to print to my printer, right? And we were trying to do it through a cable. So I pulled out my bundle of cables, and as I was packing them up and putting them away, my pen got caught up in the pile of cables and got stuffed in there. I'm excited to report I thought of that and didn't just happen upon it. Okay, did you guys get it? Okay, so let's try this. Come on, baby. So we've got CaF2, and this is going to dissociate into a Ca2 plus, and this is equilibria. Are we okay with that? You're good? Okay. Here then, and you look at it and you're like, hey, that was pretty straightforward. But here, guys, represented on the board is the very reason you're going to screw these up on the AP test. because we've done equilibria before, weak acids and bases. And eventually we're going to icebox this thing, and eventually we're going to talk about the common ion effect, and all the things that we've applied to equilibria, we're going to apply to this. But guys, there's something in what's written up there in red that is going to mess you up when you solve these on the test. What is it? Something you've never seen before as it relates to ice boxes. Do you see it?
It's the reactant.
Okay, but more specifically,
The reactant doesn't have a concentration.
that's true. Good, and we're going to get to that in a minute, but it's even more fundamental. Did you see it, Caleb? This. Guys, that is going to screw you up. You have never done an ice box where it hasn't balanced with all ones. Why is that? All of the acids that we deal with in this class are monoprotic. And all of the bases that we deal with in here are monobasic. And so, guys, you have never done an ice box with a relationship that balances with anything other than ones. And that is going to screw you up. Because what's going to end up happening is not only will this double the concentration of fluoride, but watch what happens in the Kc expression. And Spencer, this is getting to what you just mentioned. Now, guys, let's do the Kc expression. So products on top, right? So that would be the concentration of Ca2 plus and the concentration of fluoride squared. Now, guys, what goes in the denominator? Spencer already picked up on it. What goes in the denominator? Nothing. Because, guys, this is a heterogeneous equilibria. Over here on the left, you have undissolved salt. So there is not a denominator to these because solids, remember in liquids, don't go in Kc expressions because they don't have pressures or molarities. So guys, that would be the Kc expression, but we don't call it Kc, we call it KSP. Is this on the equation sheet? Not that it needs to be, because you could easily come up with it. It is not. But that's fine, because really all it is a Kc expression where your reactant doesn't belong in the equilibria. Yeah?
So you said liquids also right?
Liquids you exclude from Kc expressions. Not, did you say put it down as a 1?
Like for example, the denominator is a 1 it's all over 1, so it's
Yes, but the manifestation of that is don't include it in the Kc.
my question is then how come in Ka is we include the undissolved CH3CO?
Because it is dissolved. Yeah, so let's talk about that, because that's, guys, Josh is taking us in a different direction, but this is critical. And this is changing gears, but when we write the Kc expression, which would be a Ka, when we write the Ka for this is the Ka for the weak acid acetic acid, right? This is dissolved. It's just not dissociated. So dissolved means it's surrounded by water molecules and it's been carried off into solution. So for example, the lab that we just did 20 minutes ago, right? You came up to the front of the classroom and you got from that squeeze bottle some acetic acid. And there was no solid or liquid in that no acetic acid liquid in that beaker or whatever you got it in. What you had in there was acetic acid molecules dissolved in water. So this is aqueous. And then these are also aqueous, but also dissociated. So acetic acid dissolves in water, and then some of it breaks apart into ions. Is that okay? That's different than this. If you saw this, what you would see is you would see water with a pile of calcium fluoride at the bottom, and a little bit of it would be up in solution as calciums and fluorides. So this part of this does not dissolve. This is a solid, unlike the acetic acid, which is aqueous but not dissociated. No, there cannot. If a salt dissolves, it also dissociates. Because remember, in order for a salt to dissolve, the ionic bonds in the lattice have got to break apart. In order for acetic acid to dissolve, because acetic acid is a solid in its natural form, in order for acetic acid to dissolve, the intermolecular forces that hold the molecules together break, but the covalent bonds don't break. So dissolving this is a breaking of intermolecular forces. Turning it into this is breaking covalent bonds. Whereas dissolving salts, you don't have, when you dissolve salts, you don't have different forces holding it together. It's just ionic bonds, and either they break or they don't. Is that okay? Yeah, go ahead, Carson. Solubility product. Yeah, and interestingly, it makes sense, right? Because these will always, product is multiplication. These will always simply be multiplications. There will never be a denominator, because the denominator would always be the undissolved salt. So they're always products. Does that make sense?
Well, I was just thinking that it would be like the opposite of related normal case you have products and reactants, but it's just products.
Yeah, but that's what it stands for, solubility product, because the math is always multiplication. Is that okay? So guys, try this then on for size. We talked about this 2. So why is this 2 going to be dangerous? And the answer is this. This 2 will, yes, affect the concentration, but it will also affect the math in that it's a squared relationship. So that 2 will bite you twice. It'll get you here if you don't double the concentration, and it will get you here if you don't remember that it's an exponent. And guys, that is the most common mistake that people run into in these KSP problems, is those coefficients come back and give you the double whammy, and if you don't apply them in both instances, you get in trouble. So watch out for those coefficients because they will sneak up and get you. So with all of that said, we now understand that the KSP for this is simply the product of the products, because there is no denominator, because that's a solid, and we understand that that's the case again because the CAF is a solid. You guys good on those ideas? Let's do some math. So guys, check that out. Look at what the KSP is for calcium fluoride. 10 to the negative 11th. Guys, how much calcium fluoride is going to dissolve? Pretty stinking close to none, right? We would treat calcium fluoride as if it's insoluble. And we're going to figure out the solubility of this in a second. But guys, you're going to find out it is not very much. For all practical purposes, this doesn't dissolve, other than the fact that a little bit of it dissolves. So the question is this. The KSP for calcium fluoride is this. What is the solubility of calcium fluoride in grams per liter? And I'll give you a second to write it down, and then we'll solve this together. So while I'm waiting for people to write this down, if you want to set up your own icebox. Did you get it? Am I at least okay to switch to a clean screen? Because obviously I can't solve this down here. Is that okay? Okay. So what do I need to do? Oh, I need the magic W button. Okay. So I've got the notes in front of me. Hopefully you've got it in front of you as well. And guys, in order to solve this, what we're going to need is to set up an icebox. So we've got CaF2 is in equilibrium with Ca2 plus and 2 fluoride minus. And we're going to icebox this. But guys, notice how very little information we're given. What's the only bit of information we're given? KSP, and that's it. So guys, with that said, I would suggest that we take a minute and be clear on what we're solving for. So the question says, what is the solubility? In what units? Grams per milliliter, right? So guys, I'm going to make that a little placeholder. Oh, I don't like the way I wrote that. Guys, we're going to make that a little placeholder down here, and we're going to go grams per milliliter. So we're going to know that when all is said and done, we're going, was it grams per milliliter or a liter? Liter, sorry. So it's grams, I was going to say that's an unusual unit for solubility. So grams per liter. Okay, so when we're all said and done, we're going to figure out how much of this stuff dissolves in a liter of water. And again, all they gave us was KSP, which doesn't tell us it doesn't fit anywhere in our icebox, right? So what can we do with our icebox? What do we know? What can we assume? Joey? Exactly. Initially, there's going to be none, right? Before this breaks down, there's none. Now, guys, what do we do with CaF2 initially? Is it 0? It's squiggle. Guys, CaF2, not only, it's not that it has no molarity, it's that it doesn't have the potential for a molarity. In the same way that when we did ice boxes with weak bases and we crossed out water, because water doesn't fit in the Kc expression, guys, the same thing here. CaF2 is not a part of the conversation. So why do we include it in the icebox at all? Because if it wasn't there, the equation wouldn't balance. But guys, it doesn't do any part that we need to keep track of. So now we can continue on from there. What else can we include in our icebox? Plus x's. So guys, yeah, good. So we know that as this goes to equilibrium, this will go up by x. What will this do? Up, good, up by 2x. So therefore our equilibrium amounts, concentrations, will be x and 2x. Now this is starting to feel familiar. So now what we can do is we can set up our KSP expression, and we can say that KSP is equal to Ca2 plus, guys, don't forget to do this part, and F minus squared. Then, guys, we know that KSP, what was it? Oh, so 3.9 times 10 to the negative 11th. Guys, this is the part you're going to screw up. Go slow. This is x. My bike is done. And this is 2x squared. Now guys, forgive me, I'm not trying to belittle your algebraic chops, but a not insignificant portion of you are going to write this for that value. Some of you already did that. Guys, it's not 2x squared, it's 2x the quantity squared. So you're not just squaring the x, you're squaring the 2. See, there's that double jeopardy. Because when you evaluate this, what does the right-hand side of that equation become? 4x cubed, right? And that is equal to 3.9 times 10 to the negative 11. And so then, guys, we can evaluate this for x. If I can get my calculator out of grading mode. So we have 3.9 times 10 to the negative 11th. Divide that by 4. And then take the cubed root of that. I'm just going to write this out as a decimal. 0.00021. Can you confirm or refute? Is that okay? Okay. So now, guys, let's have a conversation. Because what you're going to find out when you solve these problems in homework, on the test, on the AP test, they're all pretty much going to start like this. But from this point, they can drag you down a bunch of different paths. So notice the path that they are dragging us down right now. They want us to figure out the solubility in grams per milliliter. What you'll also see is, what is the molarity of calcium ion? Or what is the molarity of fluoride ion? They like to do those. Or what is the molarity of calcium fluoride? So let's see if we can answer these questions. So guys, what is that value right there, the 0.00021? Where does it fit in the icebox? It's x, right? It's this. So that value represents what? The molarity of calcium ion. So what, therefore, would be the molarity of fluoride ion? Twice that. But now, guys, this is the one that gets people thinking a little bit. What if they ask you for the molarity of a saturated calcium fluoride solution? What would it be? Because do you guys, maybe I should back up. Do you understand that this solution is saturated? How do we know that it's saturated? That goes to Josh's conversation. Guys, we know this is saturated because of what this looks like. There's undissolved calcium fluoride sitting on the bottom of the beaker, which means all of that could dissolve has dissolved, so we know this is a saturated solution. So, what if they ask us the question, what is the concentration of a saturated calcium fluoride solution? What's the answer? It's this. Do you see why? Because, guys, that is, can I do this? Yes. Guys, that is the one more zero. That is the molarity of calcium ion, right? But where did the calcium ion come from? From the calcium fluoride that broke apart. And so for every calcium ion that's in solution, one of these broke apart. So that 1-to-1 ratio tells us that this is a 0.00021 molar solution of calcium fluoride salt. Does that make sense? So it would be 0.0021 molar in this, the same in this, and then twice that in fluoride ion. Do you want to talk about that, or is that okay? Understanding that none of that answered the question that we're being asked. Because the question that we're getting is, what is the concentration in grams per liter? Or I'm sorry, the solubility in grams per liter. So how are we going to find that from the information that we've got? Good. So we know this. Let me switch colors so it stands out a little bit. We know that this solution is 0.0021 moles. Oh, thank you. Come on. Moles of Ca, because I'm really pushing this pen, of CaF2, and that is in 1 liter of solution, because as Ayumu is suggesting, that's moles per liter. Now what we want to know is grams per liter. So we've already got the denominator nailed down. What do we have to do to convert to grams per liter? We need to know the mass of calcium fluoride. And what is the mass of fluorine? I don't know. 19? So 2 of those. Calcium's 40.1. So 78.1-ish. So 1 mole of calcium fluoride is 78.1 grams. So we've got that 0.00021. So guys, what that means is there is 0.016 grams dissolved in 1 liter of solution. Do you buy it? You okay? Okay, so guys, let me read the next question. Okay, I needed to remind myself of the next question so I can sort of tee this ball up for you. So guys, beyond the fact that we've got that nasty 2, and beyond the fact that we've got a component that doesn't show up in the Kc expression, this is just like equilibria we've done before, right? Iceboxing and solvent. So much so that this also has the potential to exhibit common ion effect things. So guys, let's remind ourselves about common ion effect. What does the common ion effect do to the solubility of a slightly soluble substance? Does it increase or decrease the solubility? Let's say it this way. When we talked about it previously in the context of weak acids, so we've got let's go back to our picture. Help you make the connection. So guys, here is our weak acid, acetic acid, right? What could we add to this to leverage the common ion effect? Sodium acetate, right? So if we add some sodium acetate to this, what does that do to the strength of the weak acid? Does it increase or decrease the strength of the weak acid? Decrease, right? Because if we add a bunch of this, Le Chatelier's principle says if this goes up, it drives the equilibrium to the left, thereby decreasing the amount of acetic acid that's dissociated, and by definition, that makes the acid weaker. I'm nervous that you don't seem comfortable with that. You okay with the idea? Okay. So guys, how does that apply here? Well, the same thing can happen with slightly soluble salts. If we add another salt to this solution, and if that other salt contains either one of these ions, and thank goodness, the only salts that we have to talk about are soluble salts, the ones that are strong electrolytes that dissolve completely. But guys, if we add a salt to this that dissolves completely and shares an ion, what is that going to do to the solubility of calcium fluoride? Drive it down. So for example, if we take this solution and if we add calcium nitrate, what does that do? What does it change about the equilibrium? Calcium ion goes up, the equilibrium goes left, and less of this dissolves, right? Okay, so what if we squirt some toothpaste into this thing? Guys, toothpaste contains sodium fluoride. Fluoride makes the enamel on our teeth stronger. But if you were to squirt toothpaste into this, that shouldn't be a 2. If you were to squirt toothpaste into this, you are adding sodium fluoride to the system. Sodium fluoride is a strong electrolyte. It breaks apart. You add fluorine, same thing. It drives the equilibrium that way. You get the idea? So you understand it conceptually. Let's do it mathematically. So guys, the question reads like this. Calculate the molar solubility. See, we just did the grams per liter solubility. Now we're going to do the molar solubility of calcium fluoride in a solution that's also 0.01 molar in calcium nitrate. And guys, this term molar solubility may sound foreign to you. Understand what it's really saying is just what's the molarity of a saturated solution. So if you saturate a solution of calcium fluoride, but that solution is already 0.01 molar in calcium nitrate, what is the molarity of the calcium fluoride? Do you see where we're going with this? You okay? Did you get to write it down? All right. So guys, let's hippie skip over here and let's take a swing at this one. Oops. Okay, so again, we need an ice box. So we're going to go calcium fluoride dissociates into I don't even know what I'm doing now, and fluorides. Can you imagine when I used to do this and strong titrations all in one day? No. So guys, now let's set up our ice box. Once again, we don't have to talk about calcium fluoride because it's not a part of our KSP expression. But now, guys, referencing back to our original question, remember previously, Joey pointed out that our initial concentrations are 0 in the previous example because nothing is dissociated yet. But now we realize we have an initial concentration of calcium. Now, guys, be really careful here, and maybe we should talk about this. This is the molarity of the salt. What is the molarity of the calcium ion? That's the molarity of the calcium nitrate. What is the molarity of the calcium ion? It's the same. Now, guys, what about this? I should do this. What if the salt was calcium phosphate instead of, no, Ca3. There we go. What if the salt was calcium phosphate? What would the molarity of calcium be? Triple that. Is that okay? Be careful. Guys, you should be realizing that these KSP problems are number games. And you got to be on your toes. You've been lulled into this complacent idea that everything balances with ones because everything's monoprotic. Be careful. But for now, it is 1 calcium. So, where then does that fit in here? We have, is it 0.01? Okay, where does that go? Initial concentration of calcium. So we've got an initial concentration of calcium of this. Fluoride is that. Again, we understand what's going to happen as this goes to equilibrium. This will be plus x. This will be plus 2x. So this will be 0.010 plus x. And this will be 2x. Now, guys, again, we write out our KSP expression. And I'm going to take the time to do this because we've got to get used to being careful of numbers. And this time I'm going to work to the right just to give myself some more space. Was it 3.9 times 10 to the negative 11th? Is that right? Oh, crap. Thank you. Not only, yeah, right? That should not be there. There we go. So 3.9 times 10 to the negative 11th is equal to, and now guys, look at how this changes. 0.010 plus x times 2x squared. There you go, right? So guys, what does this plus X represent? The formation of calcium ion from where? The dissociation of the calcium fluoride, and given the KSP is on the order of 10 to the negative 11th, how much is that going to be compared to 0.01 molar? Insignificant. So we can say then 3.9 times 10 to the negative 11th is then approximately equal to 0.010 times 4x squared. So now we have 3.9 times 10 to the negative 11th divided by 0.01 divided by 4. Take the square root. And I get, I'm going to write this out for effect, 0.00003 molar. Is my math okay? Kind of got ugly with significant digits. It should be too. But guys, let's talk. Let's be sure you're clear on this. What does that number, 0.00003 or whatever, what does that number actually represent? The molarity of calcium ion. Understand that it is also then the molar solubility of calcium fluoride, because they exist in a 1-to-1 ratio. For every one of these that exists, so I kind of misspoke. It doesn't directly represent the concentration of calcium ion. It's the concentration of calcium ion that's the result of this breaking apart. That's a better way to think of it. So guys, this amount is this amount, but this amount is the amount of this that broke apart. Do you see the connection? So therefore, guys, that does in fact tell us the molar solubility or the molarity of calcium fluoride, because that's how much breaks apart. Now guys, remember what we said. Adding the common ion should decrease the solubility of calcium fluoride. So this is 4 zeros and a 3. What was it without the common ion? 3 zeros and a 2. So the solubility of the calcium fluoride dropped by an order of magnitude. It dropped by a power of 10. This is 0.0002, and now it's 0.00003. So as we expected, the solubility decreased, in this case by a factor of 10. Do you get it? You guys good? Okay, so guys, we are going to give you some time. I'm going to give you some time to work on this homework. We have about 25 to 30 minutes. Here's what, and I don't know if you'll get done, but if you do get done with the homework today, and if you'd like to, and you have your Princeton book with you, you could grab your Princeton book and do some of the big idea number 2 and count it towards your hours, right? Because it's time that you could have spent doing something else that you chose to do in review. So guys, if you have time at the end, I'd encourage you to do it. It's a great idea to spread out your review. So we will grade this on Thursday. We will do week titrations on Thursday. Guys, right now that means that our test over this unit will be on Monday. I doubt that's going to happen. Let's just plan on that not happening. This is a big test and we won't fit it in during the short period. So I think we'll get done with all of week titrations on Thursday. It's typically not a multi-day thing, but then we'll find something else for Monday, and then we'll take this test on Wednesday. Okay? All right, go get them, guys.